this is the first step. The second step to describe the function. And third step is to use X. So this X can be used to denote the original equation. So we can write 0, 1, something like this. Because there are two variables, we have to use 0, 1. And it will give you an approximate solution to the original equation. And if you substitute the result back to the original equation, you will find the error like this. And we can recall the Cauchy analytical method we used earlier. We have an accuracy of minus 30, 10 to the minus 30. Cauchy. We recall that part. If we run that part, we can have accuracy of this kind of very small error, with very small error. However, with use pure numerical measure, we may have accuracy of minus 9, 10 to the minus 9. So the accuracy of this method is significantly lower than that of Cauchy analytical solution method. And if we select the initial search point, we will get a result like this. Two of the values are positive. If we change, I'm not quite sure how to change it. Yes, we got the result. If we change the initial search point, we can get a different value here. And again, if we substitute it back to the original equation, we see that the error is still very small. So we say that these two equations, so these two solutions are the solutions to the original problem. And apart from these two, if you try different values of initial searching points, you may not get other solutions because the original solution, the original equation I have shown earlier, there are only two real solutions. Using this measure, you cannot find the complex solutions. You can only find the real solutions. For this equation, you can only find these two solutions, no matter how you change the initial points. So in this way, you can first convert an original equation into this format, and then you can describe it, and then you can solve it, and finally you should verify it. These are the 4 steps we use in solving ordinary nonlinear algebraic equations. And it seems that the accuracy of this method is quite low. So our question is, how can we modify the solution so that it will be more accurate in this? If we are not quite satisfied with the results, we have to define ways to get more accurate results. Let's see how. There is a control variable or a control template in solving a nonlinear equation. So the template itself or option itself can be obtained by calling optim set function. OPT equals to optim set function. And we see that there are quite a lot of components in this template. They are always used as default values. And of all these components, we may not define that this one, I will explain it graphically later to you. This one is useful in controlling the accuracy of the solution. This one and this one are useful in improving the accuracy of the solution. Again, by graphical method like this, we can approach the solution in this way. Gradually approach the solution in this way. And in the course of approximating the solutions, we may have x first, x0 at this point, x1 at this one, and x2 at this point. Then we may have a value x of I, the x step, the x point is denoted as x of I. And from this point, we can find further another point, I plus 1. And we can improve our results point by point. And now we can find the difference between these 2 points. This can be used as the Euclidean distance. If the distance is very small, it is smaller than the place specified epsilon, we say that we are quite happy with the result. So if we select a very small number here, then if this condition satisfies, then the solution process will be terminated. And this epsilon here is TOL for tolerance of x. So this one is very useful. And this one is used to denote the solution itself, the norm of the y function. If it is smaller than this one, then we say that the solution process may also be terminated. So epsilon 1 corresponds to tau FUN. And there are other important properties. For instance, we can set the display property to ITER, which will show all the intermediate results. And this is not the default one. If you are interested in the intermediate results, you can use to set the display parameter to ITER. And this one is used to define the maximum number of interventions. And you can change them independently if you like. And there are quite a lot of other properties. If you like, you can change them all. Normally, I'd like to change TOLFQN to make that enough to improve the accuracy. So how can we change it? We can use OPT command to call optimset to find the template. Then I can use opt.tolx. We can write it to a very small number. Actually, that number cannot be implemented. We just write it as a small number. But do not never expect to get accuracy like this in numerical method. Just write it. And now let's solve the original equation. Oh, sorry, we have to code OPT here. So this is the improved solution. And if we substitute it back to the original solution, we will substitute it back to the original function. We will have a higher accuracy here, but it will never reach as high as 10 to the minus 30. So this one is improved. So you can see that the accuracy here is higher, 10 to the power minus 15. It is normal. Because for double precision algorithm, we can use a number here and a decimal point here. We can only use, I think, about 50 digits. So that accuracy